Okay, in this lecture, we're going to talk about possibly making our sorting algorithms faster by the technique of counting things. And for this, we're going to look at a motivating example at first. What if you had an extremely long array that you wanted to sort, but there was a significant restriction that the array may only contain the values 0 and 1. It may not contain any other value, only 0 or 1. How fast could you sort that? We know that we could sort this in n log n time using an existing sorting algorithm such as quicksort. But here's a new approach. Suppose we simply run through the entire array in order from front to back, and we count the number of 0 values. Let's call this count C. Then we go back to the original array and we fill in the first C items from 0 to C minus 1, and we just put 0 in each of those positions because that's how many there were. And then we fill the remainder up to the end of the array with the value 1. Okay? How fast would this algorithm be? Clearly it's correct. We just count the zeros. The number remaining is the number of ones. So how fast could we do this? Well, we've made one pass to count the zeros, and we made one pass to fill in the values that we found, that we counted. So clearly this runs in big O of n time. Big O of n time, but we have an algorithm which only works on 0 and 1 values. But we can generalize this idea, and the generalization is what's known as counting sort. Okay, so counting sort, here's the actual code for counting sort. Okay, so let's just run through this line by line. Counting sort assumes that the largest value is m minus 1. So all the values are in the range 0 to m minus 1. Okay, so the arguments to counting sort are the array A, the number of items n, and the value m, which is one past the largest value. So the first thing that we do is, instead of counting just one value, like the zeros that we counted before, we're going to count all m values. So we'll create a vector of counters. There are m of these, and they are all initialized to 0. So that's why we have m counters, each with the initial value of 0, since we haven't counted anything yet. Then this loop simply runs over the entire array and says for each value, let's use that value as an index into the counters array. So a sub I is an index into the counters array, and let's increment that counter. So we count all the zeros, all the ones, all the twos, up to m minus 1. After we've counted everything, then we have, notice here, two indexes, I and j. The purpose of I is to record our position in the output array, and the output array is still A. And the purpose of j is to keep track of the value that we are counting. Notice that j ranges from 0 up to m minus 1. Okay, so j starts at 0. And this inner loop goes over the number of times that we saw counters, or the value j. So the number of times that we saw the value j, we put that into our array A. And then we move on to the next value j for j equals 1 and then j equals 2. And each time we're putting that j into the array A. What is the analysis of this algorithm? Okay. The analysis of this algorithm is big O of n. Why? Well, clearly we have a big O of n loop right here. But it's not just n, it's also m. And why is that? Well, clearly we have a big O of m loop right here. And if m is large, then that could be significant. What is this loop? This loop is big O of m, because it stops after m iterations. And we don't know how long this is going to go, but we do know that the total number of things that we counted was n. So overall, this is order n over all outer iterations. Okay, so again, we have order m plus n, and we have an m plus n. And again, this n does not multiply times the m because this is over all the outer iterations. Okay, so the running time of this algorithm is n plus m, which seems like it could be significantly faster than n log n that we've seen before. And this is true, particularly if m is very small, like in our binary counting case, m was 2. If m is very small, then this could be a very fast sorting algorithm. In contrast, suppose that m is very large and n is very small. So we have a very short array with very large values possibly. Well, then this is not likely to be a very fast sorting algorithm compared to an n log n sort. So there's a trade-off here, depending on the value of n, the length of the array, and depending on the value of m, the size of the largest value. Depending on their interplay, counting sort could be extremely fast, linear time, essentially in the length of the array, but it might be much slower if we have not much of a restriction on the values, if m could be very large. So that's our trade-off. Okay. Now, one of the things that I want to ask is why what? Why is this faster than n log n? Well, because it's not a comparison-based sort. Notice in this counting sort algorithm, the sorting is essentially done here. And here, we're not actually comparing values using less than. We're not comparing elements of the array A using less than. We're just using array A or element A sub I to index into the counters. And so we know exactly where each item should go relative to each other. Okay. So this is not a comparison-based sort. So if we step out of the bounds that we talked about before of comparison-based sorts, then we can effectively go faster than n log n, the speed limit that we looked at before. Okay, so let's take a look then at what this algorithm actually looks like, how it behaves. And again, we'll look at visualgo.net, and we've got counting sort pulled up. Here's an unordered array, and we'll see the counting going on at the bottom, and then the replacement going on as it moves back up to the top. So here we have a bunch of counters. We're essentially putting everything into these counters down below, and then we loop over them. And let's do that one more time, a little bit slower, and see. We're placing each value directly into its counter position. And we don't actually have to copy these things, right? We're just incrementing counters according to the values. And then we iterate from left to right over these counters. Those are the values, the counter values 1 through 9, or 0 through 9. And we place them back in the original array in that order. Okay. Now, when you are dealing with alternative non-comparison based sorts, counting sort is a natural choice. Other related sorting algorithms that you might be interested in, if this sounds interesting, are bucket sort, where instead of counting each value, we might count buckets of values at a time, or radix sort, which sort of sorts the most significant bit of all the values, and then within each group of the most significant bit, which there are 2, then you sort the next most significant bit, and so on. And both of these algorithms are not comparison-based, and so have different runtime properties than what we're talking about here, than we're talking about with comparison-based sorts. So it is possible to sort faster than n log n, but we have to change the paradigm under which we're sorting.